Okay, so we were discussing priority queues, that is heaps, and today we'll discuss the final algorithm of the heap algorithm of the heap data structure. So let's start the heap sort algorithm. So that's a special algorithm that is very simple and an efficient sorting algorithm. Before going into the heap sort algorithm, let's just take a little recap. We discussed this build heap function, and here is the code for that function. And what we did was that we simply considered this array of data as a tree, and what we did was that we got the height, the length of the array, and started from the half of the length. That it means that what we did was essentially, if we have this tree, what we did essentially was we divided the index of this last element by 2 and found its parent and started our loop from this parent, from the index of this parent node. Then what we did was we called heapify on this node, and it was heapified down to move it to its respective location. For example, if this is a bigger value than its child, then this value would go down and the child would take its place. Similarly, we then move to the node on the left of this first parent, then we move to this second parent, and then we similarly move back to the root node. So the idea was that we moved from right to left from the second last level, and then we moved back on the upper level, and eventually we reached the root level. So this was the idea how um, we call this heapify function on every parent node and try to adjust the value that is on the parent to reach its respective location according to the magnitude. So this was the build heap function. And when we call this, for example, this heapify function or populate down function on this specific node, the maximum time or maximum number of steps that it can take is the length of this branch down, from starting from this point. So we can just add these values and find that the build heap function is calling the heapify function on n by 2 nodes. And if we just naively take the cost of that heapify function as log n, log base 2 of n, then this is the cost of the build heap function, and we can simplify it as log base n into log base 2 of n. So this is what we can do. Um, but you need to keep this cost in mind. So let's move on to the heap sort algorithm. Heap sort algorithm is actually a very simple algorithm, and the overall idea of this algorithm is that we start to sort our data by first creating a heap from that array. So this essentially means that we call the build heap function on the array. Then what we do is that we sort the data using that heap in a way that we just, for example, if we have an array and we have a heap, if we just delete its minimum value or the maximum value, the heap would adjust itself, and we get the value that is the, for example, minimum value. And if we keep popping the value or keep taking the values out of the heap, we'll get the values in the ascending order. If we have the max heap, then it would be in the descending order, but if the for the minimum heap, min heap, it would be in the ascending order. So let me write it here. If I create a min heap in this first step, and I take out n values from this heap, I would get the data in the ascending order. And if I just create a max heap, then I would get the data in the descending order. So this second step essentially means is that I take out data and store it somewhere that the data is sorted in the second location. So in this specific algorithm, what we do is that in the heap sort algorithm, this is the first implementation that is using a separate auxiliary array to store the data. So as I mentioned earlier, the idea is that I create a separate array to store the data, and this array should be of the exact same length of the input array. Okay, so this input array it does not necessarily mean that this is a heap. This is simply a randomly initialized array, or the data that we have received from the user is stored in this array A. So what I did is, is that what I've done is that I have simply created another array. Then I call this build heap function on the array A. That is the input from the user. Now I have this array in the form of a heap, and I just run a loop starting from the index 1 to the for example, length minus 1 means if I have of an array of, for example, 50 length, I just skip this index number 0 and start storing the data starting from index number 1 in the heap. So starting, if I start from index number 1 and the length of the array is 50, then it means that um, I have actually, for example, this would return if index 0 is free and 50 elements are stored, then this length of A would return in value 51. So I start from index 1 and I keep running the loop for 50 elements, starting from index 1 to 51 minus 1, which is 50. So I deleted 50 elements from this heap, and I stored the value that was deleted on the index I of array B. So I hope you get the idea that I pick one value from here and store it in another array B. This heap would maintain itself. That is the next minimum value or the maximum value that would take the place of index number 1. Then I would again in this loop delete that value and store it in the next index of this array B. So this is the way that I pop the n elements from the heap and store them in the array in the same order. And then at the last step, what I do is that I copy the elements from the array B into this array A. So if I just take the cost of this element, this last step, that is the n steps, then if I take the cost of this step, this delete mean actually adjust the heap as well. So that essentially is a log base 2 of n step, this one call. And I run this loop for n number of times. So it means the cost is n times log base 2 of n. This is the cost of the loop. And then I copy the data back, that is plus 1, plus n. And the cost of this build heap function was, again, I just told you that it is, we just saw that it's log base 2 of n. So the overall cost is 2 times log, 2 times n log base 2 of n plus n. And I can drop the lower order terms, that is n, and I can also drop the coefficients here. So the cost of this heap sort algorithm is n log base 2 of n. Instead of going into more details of this algorithm, let's just improve this function, this implementation of this heap sort, and just try to drop this auxiliary array, which means that what we want to do is that we want to do an in-place sortings. This in-place sorting means that we do not use any separate memory. Instead, we just use the memory that was used to store the data, and we just shuffle the data in that memory and sorted the data on the same place. So this is a better implementation. We receive this array A. We call the build heap function, that is n log base 2 of n. Now we have a heap. We simply, what we do is that we started from the last index of the array. We started from the last index, and what we did is, what we've done here is that we simply swap that element with the index number 1 element. Okay, so initially when we build this heap, we build a max heap. That is an important point here. This is a max heap. In the previous algorithm, the heap that we built in the first step was a minimum heap. In this specific algorithm, the heap should be a maximum heap, and for the maximum heap, the element on the first index is the maximum element. So we swapped that element and moved it to the last index of the array. Okay, so essentially what we have done here is that in the array, we have moved the highest element to the last index of the array. So this element is now the sorted element, and we decrease the size of the heap, which means that initially the index of the array for the heap was pointing to or saving the value of this index. Then we moved it one step back and we said that now this points to this specific index. And we called, when we swap this index, these two values, what we essentially had that the maximum value went to the last index, whereas the an arbitrary value, any value that was on this index that is definitely a smaller value, it moves to the index number one. So what we did here is that we call heapify on this index number one to move this value to its respective location, and we keep doing that for n elements. Okay, so here we did it for n minus 1 element. We do not need to sort the last element that is here on the first index for the last iteration, because if I move all the larger elements towards the right of the array, then this index on this element on the index number 1 is definitely the smallest element, and I do not need to sort it. So I actually skipped one iteration of this for loop as well. So this algorithm is actually better from the previous one in two terms, because for the first part, it does not use a separate array. Okay, so it sorts the data in the same memory that was already allocated for your program, and secondly, it actually skips another iteration of the loop as well. So let's see how this complete algorithm works using a specific example. So let's say we have this array. This is the data that is input by the user. The first step is we say that this array, just remember that this array is starting from index number one. Okay, so we would just ignore the index number zero of this array. If we specifically talk about the C++ implementation, then we will skip this index and we run our algorithm around index number one. So just considering this array as a tree, we have this binary tree structure that 16 is the root node, 4 is the left side, and 7 is the right side, and so on. So first we considered this array as a binary tree. Now what we have to do, if you just recall the algorithm, what we did was we called build heap function on this array. So let's see how this build heap function works. So initially we had this specific array. You see, this is the starting point. So in the build heap array, what we do is that we simply pick the first parent, that is the parent of this last element. This is index number, element number 7. And we called heapify on this specific element. And this time we are creating a max heap. So after comparing the 7 with the 19, 19 is a bigger value. So for a max heap, bigger values should bubble up and the smaller values should go down. Okay, so 7 would go down and we would reach here. 19 and 7 are swapped. Then we check this second, or what we can simply say is that we move on one index before this index number 3. So we move to index number 2, and on index number 2 we compared, when we call heapify on this element 4, we find that the maximum value among the children is 12, and this 12 we swap this 4 and 12. So this is the heap after two swappings. Then we move one index back, further back, and we move to index number 1. So this was index number 3. We move to index number 2 here. Now we are calling this heapify function on index number 1. So when we compare the children, this value 19 is the largest value, so we swap 19 with 16, and this is the final heap. Okay, so in fact the heapify function actually moved further down as well, but 16 is already bigger than 7, so we stopped here, and this is the shape of the final heap. So now we have a heap from the initial array. Now and we can start getting bigger values from this heap just by calling the delete max function. So now this is the algorithm. This is the dry run of the loop that we saw in the algorithm. So what's essentially being done here is that this one, if we see this tree, it's actually this array. So the first step is that we swap the last element and the first element. So we swap these two elements. So initially we had 19 on the root node, and 7 on the last index. What we essentially have after swapping is 19, which is the last index, and 7 moved to the index number 1. Okay, so that was the first step, that we swap these two elements. Then we decrease the size of the heap. So when we decrease the size of the heap size becomes 5, and we consider that the elements after this index number 5 are sorted. Okay, so this 19 is now sorted. Then what we do is that we call Heapify on this index number 1. So for Heapify, we compare this value with its children, and we find that the maximum value is towards the right, and we swap these two values. So when we swap these two values, what we have is that 16 becomes the root node and moves to index number 1, and 7 goes to index number 3. So now again we have a complete heap, because we have already moved the smaller value that we moved up. We actually percolate it down, or heapify it down to its respective location. So 16 is now the second largest value. We repeat the same process. We swap the value 4 and value 16, and we decrease the size of the heap. Now size of the heap is 4, and then what we do is that uh, we need to call again the heapify function on this element number 4. So when we call the heapify function, this bigger value is the left child. We swap these two values, and again we have a valid heap here. Similarly, we repeat the process again. We move the last value on the root. We move this value on the root. So in the array, 1 is on the first index, and 12 is now the goes into the sorted portion. So size of the heap is now 3. Then we call the heapify function is on this value 1. After comparing, we find that the biggest value is on the right side. We swap these two values, and this is the final heap. Again, repeating the process, we move 7 into the sorted part, and decrease the size of this heap to 2. And after calling heapify on the value 1, we find that maximum value is 4, that goes to root. And then again, we take out the biggest value, and now this 4 goes into the sorted part, and the size of the heap is 1. Okay, so we do not do anything here. That was the end of the loop, because this 1 is already the smallest value, and it's on the index number 1, which means that we have all the data sorted in this array. That's the heap sort function. So that's it for the heap sort. We'll discuss, if you have any questions, we'll discuss in the next lecture.